Dear students, now we are going to see the subject linear integrated circuits. The subject code is EC3451. Under that, the topic is AC characteristics of operational amplifier. On completion of this AC characteristics of operational amplifier, the students will be able to describe the frequency response characteristics of operational amplifier, explain the stability characteristics of operational amplifier, summarize the frequency compensation characteristics of operational amplifier. For a small signal sinusoidal application, one has to know the AC characteristics such as frequency response and slew rate. Frequency response. The ideal op-amp will have infinite gain. In general, open loop gain is 90 dB with DC signal. What should be the expected gain for audio and other high frequency signal? The gain must be same, but practically it is not possible. Op-amp gain decreases at high frequency and this is called roll-off. What causes the gain of op-amp to roll off? The presence of capacitive component in the op-amp causes the gain to roll off, and the internal construction of op-amp and physical characteristics of the device. The high frequency model of operational amplifier is shown in figure. The high frequency model of operational amplifier with only one corner frequency. That means a one pole is obtained due to R0 and C in the output of the operational amplifier, and this device has a roll-off rate of minus 20 dB per decade. The open loop gain of op-amp with only one corner frequency is given by the output voltage V0 is equal to minus JXC by R0 minus JXC into AOL, open loop gain into input voltage VD. So gain is the ratio of output to input, that is equal to open loop gain divided by 1 plus J2 pi F R0 C. Here F1 is equal to 1 by 2 pi R0 C. Substitute this F1 in the gain A. So we are getting A is equal to open loop gain divided by 1 plus J into F by F1. Here F1 is the corner frequency or the upper 3 dB frequency of the operational amplifier. The magnitude of the gain is given by magnitude A is equal to open loop gain divided by square root of 1 plus F by F1 the whole square. The phase angle pi is equal to minus tan inverse of F by F1. From the magnitude and phase characteristics, the two figures shown the magnitude and phase characteristics, we have to observe that for frequency in the magnitude characteristics, for frequency F less than F1, the magnitude of the gain is 20 log open loop gain in dB. For frequency F is equal to F1, the gain is 3 dB down from the value of open loop gain, and this frequency is called as corner frequency. For frequency F greater than F1, the gain has a roll-off at a rate of minus 20 dB per decade or minus 6 dB per octave. The second graph represents the phase characteristics. So y-axis represents the phase angle, x-axis represents the frequency. At F is equal to 0, the phase angle is 0. F is equal to F1, phase angle is minus 45 degree. And here the phase angle lag at a frequency of minus 90 degree. At infinite frequency, the phase angle is minus 90 degree. For a single RC pair, the maximum phase change of 90 degree can occur. The voltage transfer function in S domain can be written as A is equal to the gain A is equal to open loop gain divided by 1 plus J F by F1 equal to open loop gain divided by 1 plus J omega by omega 1. So F is replaced by angular frequency omega. So after simplification, the gain is equal to open loop gain into omega 1 divided by j omega plus omega 1. Here we replace j omega by s. So open loop gain into omega 1 divided by s plus omega 1. For number of stages or RC pole pairs are included in the output of the operational amplifier. So there will be a number of corner frequencies. So the overall gain A is given by open loop gain divided by 1 plus JF by F1. into 1 plus jf by f2 into 1 plus jf by f3. Here the condition is f1 value should be greater than 0, f2 value is greater than f1 and f3 value is greater than f1 and f2. So now we replace the analog frequency f by angular frequency omega. So gain A is equal to open loop gain into omega 1 into omega 2 into omega 3 divided by s plus omega 1 into s plus omega 2 into s plus omega 3. Here also omega 1 was greater than 0, omega 2 is greater than omega 1 and omega 3 is greater than omega 1 and omega 2. The magnitude response is given in this graph. So initially up to the corner frequency f1, the gain of the operational amplifiers remains in 90 dB. Then after frequency f1 to f2, the gain roll off at a rate of minus 20 dB per decade. Then after frequency f2 to f3, the gain roll off at a rate of minus 40 dB per decade. After the frequency f3, the gain roll off at a rate of minus 60 dB per decade. Stability of operational amplifier. What is the effect of feedback on operational amplifier? The resistor in the feedback part of the operational amplifier. For inverting amplifier, there is a 180-degree phase shift in the output at low frequencies. The figure represents the inverting amplifier. The closed loop transfer function is given by closed loop gain is equal to A divided by 1 plus A beta. Here A represents the open loop gain. The characteristic equation is 1 plus A beta is equal to 0. The circuit will become unstable. That is, it leads to sustained oscillation. Rewriting the characteristic equation, 1 minus of minus A beta equal to 0. This leads minus A beta equal to 1. The magnitude and phase condition becomes magnitude of A beta equal to 1. So phase angle of minus A beta is 0 or multiple of 2 pi, and phase angle of A beta is pi for odd multiple of pi. At low frequency, the resistor in the feedback has no effect except producing 180-degree phase shift. However, at high frequency, for each corner frequency, an additional phase shift of maximum minus 90 degree can take place in open loop gain A. For two corner frequency, it will be minus 180 degree. For a specific value of beta, A beta equal to 1, when A is minus 180 degree. This results in oscillation, and this instability means unbounded output. That is, 1 plus A beta is less than 1 or A beta is less than 0 and closed loop gain is greater than the open loop gain. So there is the magnitude response of the gain response of the operational amplifier for three different corner frequency is shown in figure. Stability specification, gain crossover frequency, the frequency at which the loop gain magnitude of a open loop gain of into beta is unity, that is 20 log OL of F beta is 0, is called the gain crossover frequency. The frequency at which the phase shift introduced by the loop gain is minus 180 degree or n pi radian is called phase crossover frequency. Frequency compensation, in applications where one desires a large bandwidth and lower closed loop gain, stable compensation techniques are used. Two types of compensating techniques are used. One is external compensation and another one is internal compensation. External frequency compensations are again classified into two types: dominant pole compensation and pole zero or a pole lag compensation. In dominant pole compensation, a pole is introduced with the help of a resistance and capacitance R1 and C1, which is connected at the output of the operational amplifier. Here A is the uncompensated transfer function of the operational amplifier in open loop condition and is given by A is equal to A into omega 1, omega 2, omega 3 divided by S plus omega 1 into S plus omega 2 into S plus omega 3. Introduce a dominant pole by adding an RC network in series with the operational amplifier. or by connecting a capacitor C from a suitable high resistance point to ground. The compensated transfer function A dash becomes A dash is equal to the ratio of V naught by Vi. A into minus j by omega c divided by r minus j by omega c equal to A divided by 1 plus j f by ft. Ft is equal to 1 divided by 2 pi rc. Using this equation, using the above equation, A is equal to open loop transfer function divided by 1 plus j f by f1 into 1 plus j f by f2 into 1 plus j f by f3. F1 is greater than 0, F2 is greater than F1 and F3 is greater than F1 and F2. From this we are going to find the A dash. A dash is equal to open loop transfer function gain AOL divided by 1 plus JF by FD into 1 plus JF by F1 into 1 plus JF by F2 plus 1 by 1 plus JF by F3. If the condition is Ft is the smallest frequency and F1 is greater than Fd, F2 is greater than Fd and F1, F3 is greater than F1, F2 and Ft. So the characteristics is given in the figure. The disadvantage, it reduces the open loop bandwidth drastically, but there is a noise immunity of the system is improved since the noise frequency component outside the bandwidth are eliminated. Pole zero compensation. Here in pole zero compensation, the series RC network is connected at the output of the operational amplifier through the resistance R1. The uncompensated transfer function A is altered by adding the both pole and zero. So R1 represent the zero. The series combination of R2 and Z2 forms the pole. The zero should be at a higher frequency than pole. The transfer function of the compensating network is given by the ratio of output V0 by Va is equal to Z2 divided by Z1 plus Z2. Z2 equal to R2 divided by R1 plus R2. So this can be simply into 1 plus Jf by F1 divided by 1 plus Jf by F0. Z1 is equal to R1 and Z2 is equal to R2 plus 1 by J omega C2. F1 is equal to 1 by 2 pi R2 C2. F0 is equal to 1 divided by 2 pi into R1 plus R2 into C2. The compensating network is designed to produce a zero at the first corner frequency F1 of uncompensated transfer function A. So initially there is no compensation is obtained. So after the pole zero compensation, the graph is drastically decreases towards the frequency F2. The compensated transfer function is given as A dash is equal to V0 by Va is equal to V0 divided by V2 into V2 by V1, that is equal to A into R2 divided by R1 plus R2 into 1 plus JF by F1 divided by 1 plus JF by F0. That is, subject is gain A, so open loop transfer gain divided by 1 plus Jf by F1 into 1 plus Jf by F2 into 1 plus Jf by F3 into R2 divided by R1 plus R2 into 1 plus Jf by F1 divided by 1 plus Jf by F0. That is equal to the open loop gain divided by 1 plus Jf by F0, 1 plus Jf by F2, 1 plus Jf by F3. That is frequency F1 is eliminated, the corner frequency. So here the condition is F0 is greater than 0 and F1 is greater than F0, F2 is greater than F1 and F3 is greater than all the other frequency. Internal compensation. In this case, we are not using any compensation techniques. During the fabrication of IC, we are compensating and designing in the IC. The capacitor is fabricated internally and the Miller effect compensation is used. Slew rate. The rate of change of output voltage with respect to time is called a slew rate. It can be represented as volt per microsecond. So slew rate is given by dV0 by dt maximum, or slew rate is equal to I maximum divided by capacitance C. So the possible questions on AC characteristics of op-amp are: define slew rate, Describe the frequency compensation techniques of operational amplifier, explain the different types of external compensation techniques of op-amp, summarize the frequency response characteristics of op-amp. Thank you.